Welcome to this, the 11th lecture in the series on fundamentals of transport processes, where we were trying to formulate a framework for analyzing transport processes of heat, mass and momentum transfer. We were looking at unidirectional transport, that is, transport takes place only in one particular direction. As I said, in general, in a general flow field, in a reactor or in a heat exchanger, the velocity is a function of all three coordinates as well as a function of time, and that is complicated because it results in partial differential equations for the governing equations for the concentration, momentum or temperature fields. So, we are trying to solve first the simpler cases, the simple cases of transport only in one direction, and we were trying to formulate a framework for how to analyze in a common framework mass, momentum and energy transport. So, the basic configuration that we were looking at looked something like this. We were looking at transport in what is called Cartesian coordinates. Okay. The x and y coordinates are along the plane, the z coordinate is perpendicular to the plane, and we considered flat surfaces, the system to be bounded by flat surfaces at in the z direction. So, that everything, there is nothing that is changing in the x and y directions, everything is a constant in those two directions. There is transport taking place only in the z direction. I will go through the derivation of the transport equations once again, because there are some additional things that we will need as we go along in this lecture, which were not covered previously for simplicity. Okay. So, the basic shell balance equation was change in energy in a time delta t is equal to energy in within that time minus energy out within that same time delta t. Okay. This equation is valid so long as there is no production or dissipation of energy within this differential volume. Okay. If there is a production or consumption of energy, it is necessary to add an additional term in this energy balance equation. One could envisage, for example, a reaction taking place within this differential volume, and if it is exothermic, it will generate heat. If it is endothermic, it will consume heat. So, there is going to be either a source of energy or a sink of energy within this differential volume. There could be dissolution processes. Dissolution processes can also be exothermic or endothermic. One could have phase change, in which case there is a latent heat of phase transformation which has to be included, and there could even be mechanical sources of energy. For example, in a pipe, if you have a viscous fluid flowing, then there is fluid friction, shear stresses, and that itself generates heat, and all the energy that goes into pumping that fluid gets converted into heat energy and thereby increases the temperature of the system. Okay. So, in general, if one were to include these energy production or consumption rates, one would have to modify this equation to include an additional term of the form source of energy within this differential volume. Okay. So, this additional source of energy, the energy that is produced within that differential volume within the time delta t. Okay. Now, the specific form of this term will in general depend upon the nature of the production of energy in this case. So, if it is viscous heating, it will have one form, if it is due to a reaction, it will have another form. But in all cases, this rate of production of energy within this differential volume is going to, first of all, is going to depend upon the volume itself. Okay. Because if you have energy produced within a volume delta x, delta y, delta z, as I shrink this volume, the amount of conversion going on due to reaction decreases. It is going to decrease in proportion to the volume if that volume is small compared to the macroscopic scale. Okay. So, this source of energy is going to be proportional to the volume itself, and the amount of energy generated is going to be proportional to delta T. Okay. So, this additional source of energy, okay, I will write it as source, is going to be some function, okay, times delta x, delta y, delta z, the volume itself, times delta t, the time interval. Okay. Now, this S E could be in general a function of position as well as time. For example, if energy were produced due to a chemical reaction, the rate at which energy is produced is going to depend upon the local reaction rate. The local reaction rate may change because the concentration changes, it may change because the temperature changes. Okay. So, therefore, this rate of production of energy is going to depend upon the local value of the reaction rate, and therefore, it is in general it is a function of position as well as time. Okay. However, in this series of lectures, we are considering a situation where there is variation only in one particular direction. Okay. And therefore, this rate of production of energy can be written as S E of z and t. Okay. So, it is going to be a function of both the z coordinate in general as well as time. Okay. How does that change the balance equation that I had earlier? Okay. I have to add another term plus S E delta x, delta y, delta z, delta t. Okay. This additional term due to the source in this energy balance equation, and when I divide by delta x, delta y, delta z, delta t, I just end up with this energy source. Okay. So, this is the additional source of energy that appears in the differential equation. Okay. And if I take the limit as delta t goes to 0 and delta z goes to 0, this remains. Okay. So, this is the source of energy within this differential volume. Note that the amount of energy produced is equal to S times volume times time. Therefore, S is the amount of energy produced per unit volume per unit time. Okay. It is the amount of energy produced per unit volume per unit time. If the energy were produced due to a reaction, then we know what is the rate of reaction. Okay. The reaction rate per unit volume per unit time times the delta H of the reaction will give you the source of energy. Okay. In similar manner, one can get the source for other kinds of heating or cooling due to adsorption, due to dissolution, due to phase change, due to viscous heating, and all of these will have this particular form. S is the rate of production of energy per unit volume per unit time locally within the flow. Okay. So, this is the modification that we have to make whenever there is a source or a dissipation of energy, and that results in a modification of the conservation equation. Okay. And plus S E divided by rho C P. So, there is this additional source term in the energy balance equation. Okay. Now, similar source terms will appear in the mass balance equation as well. Okay. So, for example, in this particular case, change in mass in time delta t is equal to mass in minus mass out plus the source. Okay. So, if the species whose concentration is given by C, if that species is produced in a reaction, this source will be positive. If it is consumed in a reaction, this source will be negative. Okay. So, this is additional source of mass that also comes in to the mass conservation equation. That source of mass, okay, has the form is equal to some function S, which is in general a function of position, times the volume times delta t. Okay. So, if the rate of reaction is given by R, okay, so that gives you the rate at which mass is produced per unit volume per unit time within that differential volume, that is a local rate of production. Okay. So, that additional source of mass will be proportional to the volume itself in the limit as the volume goes to 0, and it is proportional to the time that I wait, because as the reaction proceeds, the amount produced is going to be proportional to delta t in the limit as delta t goes to 0. So, there is this additional source of mass that comes in due to reaction. Okay. And in this mass conservation equation, this source comes in as plus S times delta x, delta y, delta z, delta t. Okay. And if I divide throughout by delta x, delta y, delta z, delta t, okay, I get something that is equal to plus S, okay, the rate of production of mass. Okay. And this therefore gives me in the concentration field an additional production term. Okay. And this source of mass is the rate of production of mass per unit volume per unit time once again. Okay. So, this is the rate of production per unit volume per unit time. And you can see that dimensionally this entire equation makes sense. dC by dt, C is the concentration mass per unit volume, dC by dt is mass per unit volume per unit time. Therefore, S also has to have dimensions of mass per unit volume per unit time. What is the equivalent source in the momentum conservation equation? Okay. That the source in the momentum conservation equation comes in the form of body forces. Okay. I wrote in the last 2 lectures ago the sum of applied forces. Forces are of 2 types. One is what are called surface forces. Okay. At any differential volume, they act at the surfaces of that volume. Okay. And the force applied is equal to the stress times the surface area or the pressure times the surface area. Okay. So, the sum of applied forces I can divide it into 2 parts. Okay. One is sum of applied, sum of body forces plus sum of surface. Okay. The body forces act on the entire volume itself. An example is the gravitational force, the centrifugal force, various other kinds of forces such as electrical or magnetic forces. They act on the entire volume. Okay. So, if I had a body of mass m, the gravitational force is the total mass times the acceleration due to gravity. If I have a differential volume of fluid of volume delta v, then the gravitational force is equal to mass times the acceleration due to gravity. It can also be written as the density times the volume times the acceleration due to gravity. Okay. So, therefore, these body forces are proportional to the volume itself. The surface forces are proportional to the surface area. Okay. So, in that lecture we looked at surface forces, the shear stress acting on the top and bottom surfaces. I defined tau xz as a force per area in the x direction acting at a surface with outward unit normal in the z direction, and from that I got for you the forces on the top surface and the force on the bottom surface. Okay. Now, what about the body forces? Okay. Yeah. The body force will in general have the form some force. In this particular case, we are looking at momentum balance in the x direction for the x component of the velocity. Therefore, the body force will be of the form x f x times delta x, delta y, delta z. Okay. The force, the x component of the body force times delta x, delta y, delta z. Okay. So, it has the form of a force density, force per unit volume times the volume itself. Okay. If this were the gravitational force, will have the form rho times gx times delta x, delta y, delta z. Gx is the component of the acceleration due to gravity in the x direction or in the flow direction. Recall, we are writing the momentum balance equation for the x direction or the flow direction. Okay. So, therefore, the gravitational force will be rho g x, which means that for the gravitational force f x is equal to rho times g x. Okay. So, this has the form of a force per unit volume, the force density, okay, the force density times the volume itself. Okay. So, this has the form of force density times the volume itself. Okay. So, this can be put into the differential equation which I had earlier. Okay. Plus f x delta x delta y delta z. Okay. I have a similar force form here, plus f x delta x delta y delta z. Okay. And this carries through to this equation, plus f x. I am sorry, when I write this, there should be no delta x. Okay. When I divide through it by delta x delta y delta z, this delta x delta y delta z cancels and I will just get f x. Okay. And therefore, my momentum conservation equation finally is of the form this plus f x, okay, or if you divide through it by the density, f x by rho. Okay. Note once again, f x is the force acting per unit volume per unit time. Okay. I am sorry, the force acting per unit volume. In the previous cases, so force acting per unit volume is equivalent to momentum change per unit volume per unit time. In the case of mass transfer, there was a source term, mass increase per unit volume per unit time. In the heat transfer problem, there is a source term, heat transfer per unit volume per unit time. In this case, it is a force per unit volume, which is momentum per unit volume per unit time. Okay. So, this is the effect of additional sources or sinks or body forces in the mass, momentum and energy conservation. In all three cases, they have exactly the same form. Okay. Even though we calculated the momentum conservation equation by a slightly different framework from the mass and energy conservation equations. Okay. Okay. So, and then we looked at the unsteady diffusion. Okay. Of course, at steady state, if you keep the temperature a temperature difference between two surfaces, in the final steady state the solution is just a linear profile. We got that in terms of the scaled variables, T star is equal to 1 at z equal to 0 and T star is equal to 0 at z equal to 1. Okay. And the steady profiles were exactly the same when expressed in terms of the scaled temperature, concentration and velocity fields, k 1 minus z. Okay. So, having got the steady state solutions, you keep two surfaces at two different temperatures, what is the temperature variation in between? Two surfaces at two different concentrations, what is the concentration variation in between? Two surfaces moving with different velocities, what is the velocity variation in between? At steady state, they have exactly the same form. That is because the equations of motion that we got in all three cases are exactly of the same form. And then we went on to look at the unsteady problem. So, this was the problem where I have two surfaces at equal temperature. The scale temperature T star was equal to 0. The temperature in between the two surfaces was also equal to 0. Okay. So, everything was exactly at the same temperature, the two surfaces as well as the medium in between. Okay. At time t is equal to 0, I increased the temperature of the bottom surface to a higher temperature T 1. Okay. So, instantaneously at t is equal to 0, the entire fluid is still at 0. Okay. The medium as well as the top plate is still at 0 temperature. Okay. However, instantaneously I have increased the bottom surface temperature to 1. Okay. And I want to know how the temperature in the gap between the two surfaces evolves with time. At very long times, I would expect the temperature to reach a linear profile. Okay. But at very short times, initially you will have a temperature that looks like some kind of a step profile, and that will slowly evolve over time. Okay. until finally in the long time limit you get the linear temperature profile. Okay. In this case there are no sources or sinks within the volume, and therefore, the temperature equation is just dT by dt is equal to alpha d square T by dz square, okay, without the source or the sink term. And we were trying to get a solution for this in the limit where the penetration depth, okay, the depth to which the temperature field penetrates is small compared to the thickness between the plates. Okay. So, if this distance h is large compared to the region over which you have a disturbance due to the presence of this bottom plate at a higher temperature, then we can effectively consider the boundary condition to be T star is equal to 0 as z goes to infinity, because the temperature field here locally is not the top plate is too far away to influence the temperature field here locally. Okay. So, the only requirement is that the temperature field has to go to 0 as z goes to infinity rather than at a fixed value of z. Okay. So, that was the requirement for the temperature field. Okay. So, to solve this problem, the first thing we tried to do was to look for some way to scale the variables. Okay. You have a dimensional length z, dimensional time t. Okay. Now, if the presence of the top plate were important, then I would simply have scaled z by the total height h. Okay. But I considered the case where the penetration depth is small compared to h, so that the length scale in this case should not depend upon h. Okay. So, that was the basic idea. Okay. So, then I have z and t. Okay. I also have one other dimensional parameter, which is the diffusivity alpha. Okay. And from that I can make only one dimensionless variable z by square root of alpha t, okay, because z, alpha and t, 3 dimensional parameters, they contain 2 dimensions, okay, 2 dimensions L and t, and from that I can get only one dimensionless variable. Okay. So, that was the basic idea. Okay. And if this assumption is correct, then from this dimensionless variable I should be able to rewrite the conservation equation in terms of this variable alone, because once I have non-dimensionalized everything, the final equation that I get should not depend individually on z, t and alpha. It should depend only upon the parameter psi. So, that was the basic idea. Okay. And so, we got expressed T star in terms of psi by differentiation by chain rule. Okay. And after we implemented this, okay, by you use chain differentiation to express dt by dt in terms of dt by d psi, as well as d square t by dz square in terms of d square t by d psi square. Okay. So, after you implemented these two, the final equation ended up as we expected, being an equation only in terms of psi, not individually in terms of z and t. Okay. And the boundary conditions. Okay. At z is equal to temperature, the T star is equal to 1, z is equal to 0 is equal to psi equal to 0, because psi is equal to z by square root of alpha t. As z goes to infinity, T star is equal to 0, and that is at psi going to infinity. Okay, in the limit as psi goes to infinity, which is very far away from the bottom plate, the temperature should go to the temperature that was the initial temperature within the entire fluid. The third condition was an initial condition. Initially, for all z greater than 0, okay, we had imposed the condition that the temperature T star is equal to 1 is switched on at time t is equal to 0. Okay. Since it is switched on at time t is equal to 0, this temperature everywhere else in the fluid except for the bottom plate is still at T star is equal to 0. So, therefore, for z greater than 0 at time t is equal to 0, T star has to be 0 everywhere for all z, okay, except for at the bottom plate, okay, at t is equal to 0. So, that was the third condition. Now, t is equal to 0 for z greater than 0 is equivalent to psi going to infinity, because psi was equal to z by root alpha t. So, if I take the limit t going to 0, psi goes to infinity. Okay. So, when the limit as psi goes to infinity, I require that t star is equal to 0. Okay. So, clearly here you can see I start off with an equation that was second order partial differential equation in z, first order in time. I required 2 boundary conditions in z, 1 initial condition in time for getting a solution. I expressed it in terms of the dimensionless coordinate psi. Okay. Once I have done that, okay, 2 of the boundary conditions, that is one boundary condition z going to infinity and the initial condition t is equal to 0, both of these end up being identical to each other. In the final equation that I have in terms of psi, I can impose only 2 boundary conditions because it is only a second order equation in psi. So, one boundary condition and one initial condition turn out to be the same thing when expressed in terms of psi. So, now I have only 2 boundary conditions to solve for psi. Okay. And we looked at the solution for that. Okay. The solution is of the form integral 0 to psi of e power minus psi prime square by 4, okay, divided by integral 0 to infinity. Okay. This integral 0 to infinity is actually just given by, is just a constant. It is actually equal to square root of pi. Okay. This is just equal to square root of pi. Okay. So, this is just a constant and the variable psi only comes in the upper limit of integration. Okay. Now, in the limit as psi goes to 0, the temperature goes to 0. Okay. So, the temperature disturbance is non-zero only when psi is order 1. Okay. For example, if you actually calculate this function, okay, if you actually calculate this function for different values of z by square root of alpha t, okay, you will find that at z by root of alpha t is equal to 1, it is about 0.56. At z by root alpha t is equal to 2, it goes down to 0.08 and 3 it goes down to 0.04. So, it decays over a distance comparable, okay, over psi approximately equal to z by square root of alpha t of order 1, 2, 3 etc. Okay. That means that the thickness to which it penetrates is given by square root of alpha t, okay, because this temperature disturbance is significant only when z by square root of alpha t is 1 or when the thickness is approximately root of alpha t. Okay. By the time the thickness the distance becomes 3 times root alpha t, the temperature disturbance already becomes small. Okay. So, therefore, this is the penetration depth square root of alpha t. By the time the distance goes to one time that penetration depth, the temperature is already decayed to about half the value at the bottom wall. Okay. So, therefore, this is the penetration depth and initially we had assumed that the penetration depth is small compared to the distance between the plates. Okay. So, therefore, square root of alpha t has to be small compared to h. Therefore, this solution is valid only at the very initial times when t is small compared to h square by alpha. Okay. So, once t becomes of the same magnitude as h square by alpha, the fact that there is another plate there, okay, is starting to affect the heat conduction in the domain, and the presence of that other plate has to be taken into account when we solve the problem. This is easily extended to heat transfer problems. Okay. I have T1 at the bottom. I have a domain in which T is equal to T naught, T is equal to T1, and T is equal to T naught everywhere for time T less than 0. Okay. There is the exact analogous heat transfer problem, and you get the exact analogous solution. Okay. You can actually you can actually get the flux as a function of time, and you can see that the flux actually goes as 1 over square root of alpha t. Okay. The mass transfer problem. exactly analogous. I have two plates with equal concentration of a solute, C star is equal to 0 everywhere in both on both the surfaces as well as within the fluid for time t less than 0. Okay. At time t is equal to 0, I instantaneously change C star to a finite value 1, okay, and then I want to know how the concentration field progresses with time. Okay. And in this case, I get the exact same solution, C star is equal to 1 minus this whole thing. The only difference I do is to replace alpha by d, the thermal diffusion the mass diffusion coefficient, okay, within this expression. Exactly the same for momentum conservation. Okay. So, I have a fluid which is initially at rest, both surfaces are at rest. At time t is equal to 0, I instantaneously start moving the bottom plate with a velocity u. Okay. In terms of the scaled velocities, I get the exact same solution, except that instead of the mass diffusivity, I have the momentum diffusivity or the kinematic viscosity here. Okay. That is the only difference. So, the solutions when expressed in terms of the dimensionless temperature, concentration, velocity are exactly the same, except that you have to use the appropriate diffusion coefficient, whether it is mass diffusivity, thermal diffusivity or kinematic viscosity, as the case may be. Okay. So, in all three cases exactly the same. And last class I had also actually solved for you a problem which is not exactly unidirectional flow. Okay. I had solved for you the problem of the diffusion into a falling film. Okay. And in this case, the flow is the transport is not unidirectional. There is transport both in the z direction, the cross stream direction, as well as there is convection due to the mean flow downwards in the x direction. Okay. And so, you have to write two boundary conditions for z is equal to 0 and z goes to infinity. Once again, we are assuming that the penetration depth is small compared to the thickness of the fluid. You also have a condition that the concentration goes to 0 at the very entrance of the channel, because the fluid has not yet come into contact with the gas. Okay. But we wrote a differential equation for this differential volume at steady state under conditions that there is no variation with time in the concentration field. However, there is variation with respect to the streamwise direction. There is mass coming in and leaving a differential volume in the streamwise direction, and there are diffusion fluxes in the cross stream direction. We had neglected diffusion in the streamwise direction in comparison to convection. Again, we came back and saw under what conditions that is valid. So, this mass conservation equation, okay, gave me a resultant equation that was exactly the same form as the unsteady equation, except that instead of dc by dt, I have u times dc by dx. Okay. Note that u in this case was approximated by a constant velocity. U is independent of position. So, I have u times dc by dx instead of dc by dt. Okay. So, the solution is exactly the same, except I have to replace t by x by u, okay, and then I get the exact same solution. Okay. So, if I define a dimensionless variable of this form, where t is replaced by x by u, the solution that I got for the unsteady problem can be written down in exactly the same manner for this steady state problem. Okay. And I had got out that solution for you. Okay. In this case, the penetration depth is square root of x d by u. Okay. Note that in this case, this similarity variable z by square root of x d by u is not a dimensional necessity, okay, because I have now 4 parameters z, x, d and u, 2 dimensions, length and time. So, I can form at least 2 dimensionless groups. Okay. But just using the analogy between the unsteady problem and the present steady state problem, I was able to write down the solution for this as well. Okay. The penetration depth is square root of x d by u. Okay. Solution is valid only when this is small compared to the total thickness h, and we got the condition that x by h has to be small compared to a Peclet number, okay, based upon h and the mass diffusivity. Okay. there was a second condition that the velocity is nearly a constant. Okay. The velocity in this case is not actually a constant. We will come back and actually calculate the velocity field in this problem, maybe the next lecture or the lecture after that. Okay. But then there is a velocity, it is the slope of the velocity at the surface is 0, because the shear stress has to be 0 from the stress balance condition. Okay. But however, there is a correction which goes as a second derivative, the curvature of the velocity field, that is non-zero, and therefore, the variation in velocity will go as the curvature times z square, and we estimated that variation over lengths comparable to the penetration depth. Okay. And on that basis, we found the condition that dx by u has to be small compared to h square, or x by h is small compared to the Peclet number, the exact same condition that we had for the penetration depth to be small compared to the thickness h. Okay. And finally, the convective flux and the diffusive flux, the ratio of those two has to be small. That happens when the Peclet number based upon the downstream distance x is large compared to 1. Okay. So, these are the conditions. And this enabled us to get for the first time a correlation between the Nusselt number and the Peclet number for this particular problem. Okay. We calculated the average flux as an integral over the entire downstream distance from 0 to L of the local flux. Okay. And from that we got a correlation for the Peclet number of this form, 2 Cs square root of u d by L power half. Okay. And the Nusselt number had this form. Okay. So, it goes as Peclet number power half times some constant. This constant can be evaluated. This constant turns out to be approximately 1.12. Okay. So, this times Re power half Sc power half is the Sherwood number or the Nusselt number in this case. Exact same analogy will work for heat transfer. If you had a heated gas near a fluid which is flowing down, which is a cool fluid, a commonly encountered configuration in, for example, cooling towers. Okay. In that case, I want to know what is the depth to which the temperature profile goes and what is the flux of heat at that interface. I would use exactly the same result. In that case, the Nusselt number will be equal to 2 by integral 0 to infinity d psi prime e power minus psi prime square by 4 times the Reynolds number times the Prandtl number power half. Okay. So, that is the exact same analogy for heat transfer. Okay. Not a similar analogy for momentum transfer, because we have to have body forces acting on the system. We will come back to a momentum transfer problem a little later. Okay. So, that was a class of solutions called similarity solutions, okay, where effectively I have transport into an infinite fluid, okay, and I use that fact to reduce the problem based upon dimensional analysis or analogy to a dimensional analysis problem, and then use that to get a solution. Okay. How about if the channel is of finite width? Okay, that was the problem that we had started in the previous class. Okay. I have t is equal to 1 at the bottom, t is equal to 0 at the top. Okay. The bottom is at z equal to 0, the top is at z equal to 1. Okay. My differential equation in this case is going to be of the form dt by dt is equal to d square t by dz square. Okay. I had used scaling in order to reduce the number of dimensional groups. Okay. I had effectively removed the thermal diffusivity from the problem by appropriate scaling, so that I can get in just in terms of scaled variables. T star was defined as t by minus t naught by t 1 minus t naught. So, that t star is 1 at the bottom, is equal to 0 on top. Z star is z by h, it is 0 at the bottom, 1 on top. We are scaling everything in such a way that everything varies approximately in the range 0 to 1, okay, throughout the entire domain. Okay. So, that we do not have to worry about the actual dimensions in the problem. Okay. And if I put this in, I get a scaling for the temperature. Okay. Since only alpha and h are the only parameters that I have, I can get only one scale temperature T star, which is T times alpha by h square. Okay. And if I put that in, I finally get an equation in terms of the scaled variables. Okay. which contains no dimensional parameters in it. Now, in the limit as time goes to infinity, I would expect to have a linear temperature profile. Okay. We had already solved that linear temperature profile about 3 lectures ago. Okay. In this particular case, a linear profile that varies between 1 at the bottom and 0 on top is 1 minus z star. Okay. So, d square t by d z star square is equal to 0. I get the steady temperature profile as 1 minus z star. Okay. Now, I separate out the temperature into 2 parts. One is the steady part and the other is the transient part. Okay. We will see later the reason why we do this separation. Okay. It is important. Okay. It is important that we separate out into 2 parts. One is the steady part and the other is the transient part. Okay. The steady part satisfies the equation d square t steady by d z square is equal to 0 with boundary conditions t steady is equal to 1 at z is equal to 0 and t steady is equal to 0 at z is equal to 1. So, those are the boundary conditions for the steady part. Okay. The total temperature field. Okay. So, T star is equal to T steady plus T transient satisfies the equation dt steady plus T transient by dt is equal to d square of T steady plus T transient by dz square. These equations are linear in the temperature. Okay. The total temperature field has boundary conditions T steady plus T transient is equal to 1 at z is equal to 0. Okay. And T steady plus T transient is equal to 0 at z is equal to 1. Okay. Now, the steady temperature is by construction independent of time. Okay. So, the time derivative of the steady temperature is identically equal to 0. Okay. In addition, I have my equation for the steady temperature as the second derivative. Okay. So, this d square T steady by dz square is also equal to 0. Okay. Therefore, for the transient part of the temperature, I have dt transient by dt is equal to d square T transient by dz square. So, that is the equation for the transient part of the temperature. Okay. What about the boundary conditions? At z is equal to 0, T steady is equal to 1, okay, and T steady plus T transient is also equal to 1. The total temperature is also equal to 1. That means, I have to have T transient is equal to 0 at z is equal to 0. Okay. So, therefore, the transient part of the temperature has to be identically equal to 0 at z is equal to 0. Okay. How about at z is equal to 1? T steady is 1, the sum of the two T steady plus T transient is also equal to 1. Okay. Therefore, I need to have T transient is equal to 0 at z star is equal to 1. Okay. Now, for the steady part, there was no time derivative, so it was sufficient to have just 2 boundary conditions. For the transient part, there is a time derivative. It is first order in time, and therefore, you require an initial condition as well. Okay. What is that initial condition? Okay. At the initial time, T star is equal to 0, T is equal to 0 at all z. So, when I just switched on the temperature of the bottom surface, the temperature everywhere else within the fluid was equal to 0. So, therefore, the temperature is equal to 0 at T star is equal to 0 for all z. Okay. However, the steady part, okay, so this means that T transient plus T steady is equal to 0 at all z. Okay. The steady part is independent of time. Okay. The steady part is time independent, it's only a steady solution. Okay. Therefore, the initial condition is that T transient is equal to minus T steady at T star is equal to 0 for all z. Okay. So, the transient part is equal to minus T steady. T steady was equal to 1 minus z. Okay. Therefore, I require that T star transient is equal to minus of 1 minus z, okay, for all z. Okay. So, this is the differential equation. These are the two boundary conditions. This is the initial condition for this unsteady problem. Okay. Note that because we separated out the temperature field into a steady plus a transient part, for the transient part the boundary conditions are T star is equal to 0 both at z is equal to 0 as well as at z is equal to 1. Okay. In other words, we have homogeneous boundary conditions. Okay, in the two spatial coordinates for the unsteady problem. Okay. If I just had T star is equal to 0 on all boundaries, then of course, the temperature field would just be T star is equal to 0 everywhere. Okay. So, the temperature field will be non-zero only if I am forcing it somewhere, and that forcing is coming in at the initial time in this problem. Okay. So, we have a problem in which the temperature is 0 on both boundaries for the transient part. Okay. So, for the transient part alone, the temperature on both surfaces is equal to 0, but there is forcing at the initial time. Okay. And that is because even though the temperature is 1 at the bottom surface in the original problem, I have subtracted out the steady part. The steady part had temperature equal to 1 on the bottom surface, okay, and therefore, for the transient part the temperature is equal to 0 both at the bottom and the top. Okay. So, if the transient part was identically equal to 0 in the long time limit, the temperature would just identically go to 0. Okay. However, the transient part is being forced at initial time because the total temperature is 0. Therefore, T transient has to be minus of T steady, okay, and that is what is forcing the temperature field in this unsteady problem. Okay. So, how do we solve this equation? Okay. We solve it by a method called separation of variables. I have a temperature field which is a function of z star and t star. Okay. This temperature field I write it as the product of two functions, okay, z of z star times I will call it as theta of t star. Okay. My original equation was a partial differential equation. Okay. The original equation that I have here is a partial differential equation of a function that depends both upon z and t. Okay. Now, I am separating it out into two parts, one which depends only upon z and the other which depends only upon t. Okay. So, I can insert this into the differential equation, okay, and what I will get is d by dt star of z times theta is equal to d square by dz star square of z times theta. Okay. However, z is only a function of z star and theta is only a function of t star. Therefore, I can simplify this to get z times partial theta by partial t plus is equal to theta into d squared z by partial z star square, okay, and divide by z times theta, okay, to get 1 over theta partial theta by partial t is equal to 1 by z partial square z by partial z star square. Okay. Now, so now I have got the equation of this form, okay. And if you look at this equation, the left hand side of this equation is only a function of time. The right hand side of this equation is only a function of z star. Okay. So, if this equation were true, this has to be true for all values of t star and z star. Okay. What that implies is that if this equation were true, then both the right and the left hand sides have both got to be equal to constants. Let us assume that it is true for one particular z star and t star. Okay. Then I can change z star and keep t star a constant, okay, and then the equality will be destroyed, because the left hand side is only a function of t star, the right hand side is only a function of z star. So, if I change z star and keep t star a constant, only the right side will change, the left side will not change, and the equality is no longer valid. Alternatively, I could do it the other way. I could keep z star a constant and change t star, in which case only the left changes. Okay. So, the only way that this equality will be valid for all values of z star and t star is if both sides are equal to constants. Okay. So, by this separation of variables procedure, I have reduced this equation, which was originally a partial differential equation. I wrote the dependent variable t star as the product of two terms. One depends only upon z star, the other depends only upon t star. I inserted that into the equation, divided by z times theta, and I got an equation in which the left hand side depends only upon t star and the right hand side depends only upon z star. Okay. And because of that, both of these individually have to be equal to constants. Okay. So, now we have two different equations to solve. Both of them are equal to constants, and we have to solve these in the domain in order to find out the solution for the temperature field. That solution for the temperature field we will continue in the next lecture. Okay. But before we leave, let me just re-emphasize a few important points here. First thing is, I had an unsteady diffusion problem, and in the limit of long time you expect that the temperature has to go to the final steady solution for the temperature field. Okay. And that final steady solution for the temperature field, okay, is given by 1 minus z star. Okay. So, in the limit as t goes to infinity, I expect the temperature field to take a steady value. Okay. So, I separated out the transient part from the steady part. The steady part is what is there in the limit as t goes to infinity. Okay. The transient part is the correction to that steady part as I am approaching infinity. Okay. As time starts from 0 and time progresses, there is a steady part which is going to reach in the long time limit, and there is a transient part which is the difference between the actual temperature and that steady part. Okay. And the reason I did that correction was because I wanted to get homogeneous boundary conditions for t star at both boundaries here. Okay. I wanted to get homogeneous boundary conditions for both for t star, the transient part, at both boundaries. Okay. Initially, of course, the temperature is 0, which means that the transient part is actually non-zero. Okay. So, because of this I am getting a forcing at initial time, okay, and I have homogeneous boundary conditions at both z is equal to 0 and z is equal to h. Okay. And then I briefly told you the procedure for separation of variables. This one we will review once again in the next class before we go on to the solution for the entire temperature profile. So, this separation of variables procedure is the second example of how you solve this partial differential equations within the domain. Okay. The first example that I showed you was the similarity solution, where we made use of the fact that there are no dimensions, so there is a deficit of dimensions in order to convert from a partial differential equation to an ordinary differential equation. In this case, we will get two partial differential equations and we will see how to solve those. So, we will continue this in the next class. Please keep in mind what has been done so far in the separation of variables in this lecture, and we will see you in the next time. Thank you.